All right, welcome back, everybody. Today we are talking about Unit 7, Day 5, which is converting our equations from polar form to rectangular form, and then rectangular form back to polar form. In order to do those conversions, we need to call on those formulas that we've kind of developed over the course of this unit, and we wrote them down in our notes last class. All right, and we're going to refer to them throughout our lesson today. So let's see, we learned that x is the same thing as our cosine theta. We use that for finding the x component of our vector, and we also use that to find the x coordinate of a point. We know that y equals our sine theta. We know that y divided by x will give us the tangent of an angle. And we also know that the square root of x squared plus y squared will give us our magnitude, or the radius, if we're talking about polar form. This last one, though, I want to kind of change. If we want to get rid of the square root, and the square root's only there just because a lot of times we're solving for just r. But if we're doing conversions with equations, a lot of times we don't want the square root there. So I'm going to actually take this one and square both sides and write this one as x squared plus y squared equals r squared. So like the true Pythagorean theorem version of this. So these conversions is what we're going to be calling on a lot today. All right. Now we are going to use these to switch from rectangular, so anything with x and y would be considered rectangular, into polar. So anything with r's and thetas, that's considered polar. Now anything that we are doing has to be in one form or the other. You cannot have a mix of both. So anytime you have x and y, that is rectangular. And then anytime you have r's and thetas, that's polar. So this is what we did last class. We had coordinates of points. Today we're going to be talking about equations. So equations is more like things that you're going to end up graphing. Okay, so let's start off with some examples of converting from rectangular to polar. So we're going to start off with x, y, and move into our theta. So let's start with this example. It says y equals 5x. So I hope that you look at that equation and you look at that and you say, oh, that would be a diagonal line. It has a y-intercept of 0 and a slope of 5. So you should look at that and know what it looks like. Now in polar form, it's going to look a little weird to you. So let me show you how you convert it to polar form. In polar form, you would take and figure out from your conversion box, how can I make your x's and y's look like something that you see over in the conversion box? All right, there's lots of different ways you could go about doing this. One is to take the x and replace it with our cosine theta. And you can take the y and replace it with this r sine theta. Another thing that we can do is we can look at the x here and divide both sides by the x. Dividing by a variable is okay as long as you're not making it disappear from the problem. And then you can say, oh wait, I know what y divided by x is equivalent to. because we have a y divided by x right here in our conversions. All right, so you have a few options. Some make the problem easier than others. I'm going to tell you right now that probably the easiest is going to be the last one I discussed, dividing both sides by x, because it's a one and done situation. If we have y divided by x equals 5, we can take the third conversion, which tells us in rectangular y divided by x is equivalent to tangent theta in polar, then we can just go ahead and make that substitution. We know y divided by x is the same thing as doing tangent theta. All right, and once we do that, this is now a polar equation. So what we're saying is that if we graph this in rectangular, this is a line. We're saying if we graph this in polar, it's still going to look like a line. So if you graph this on this kind of graph paper, it makes a line. If you graph this on this kind of graph paper, still is going to make a line. Okay? So the pictures look the same. It's just a matter of how you would graph them on the paper. And we're going to talk about graphing next class, but we need to kind of understand how to work with the equations before we can actually graph the equations. All right, let's look at another one. Let's see. X squared plus y minus 1 squared equals 1. Now, I hope some of you out there know what shape this is when you look at it. If we have an x squared part and a y squared part, we have some curves happening. Hope somebody was like, oh, isn't that thing that we did last year in Math 3? It is, kids. This is a circle. All right, it's a circle that has a center at 0, 1 and a radius of 1. That's what that is. All right, now circles don't graph very well on your rectangular graph paper. Circles are curvy, so they graph a lot better on a piece of graph paper that's a bunch of concentric circles. So, much better done in polar. So what we are going to do is go back to our little conversion box up here and think to ourselves, which one of these conversions has some x squareds and some y squareds in it? And hopefully you're looking at that last one that says x squared plus y squared equals r squared. So we probably want to use that one. The problem is we don't have an x squared plus y squared next to each other. So what you have to do is you have to manipulate this a little bit, which does mean that you need to square this part out. So we are going to write down x squared, and we are going to do the math to square this part out and get y squared minus 2y plus 1 equals 1. And we're going to clean this up a little bit. Our 1's here cancel out, which is lovely. And you get x squared plus y squared minus 2y equals 0. Now, here comes the fun part. X squared plus y squared, we know, is equal to r squared. Now, here's where some of you, lovely students, mess up a little bit because you stop and you say, oh, I made a conversion, I'm done. But the problem with this is if you stop here, you've got your equation trying to live in two different worlds. You've got an r squared, which is polar, and you've got this y, which is rectangular. So it's like your equation's having an identity crisis. It doesn't know if it should be graphed on circle graph paper or if it should be graphed on rectangle graph paper. So you're not done with this problem yet because you need to fully go through the transformation. So what we are going to do is go back to our little conversion box, and we need to replace the y by using what y is equal to. All right, y is equal to r sine theta. So we're going to come down here, we're going to replace the y in parentheses with r sine theta. All right, and now you're going to say, all right, sweet, I'm done. No, sorry, you're not quite, because the problem can be simplified. And you're groaning at home. I can hear it through my computer screen multiple days in the past. Both of these have an r, so we can factor that out. So we'll say r, then r minus 2 sine theta equals 0. And you might be saying, but why are we doing this? Well, we're doing this because we are going to need to graph this in polar. And if we're graphing it in polar, we need r by itself. So I'm just prepping you for what's coming on the next set of notes. So we want to get r by itself. So solving for r, we're going to have r equals 0 from this part. And then from this part, you get r equals 2 sine theta. Now, you should be saying to yourself, how can r equal 0? Doesn't r stand for radius? How can you have a radius of 0? Well, you can't really, friends, because that's just a point at the center of your graph paper. And we already mentioned at the top, this should be a circle with a center at 0, 1 and a radius of 1. So we toss out the r equals 0, because it doesn't make any sense for this problem. And we box in what we have left. So what we have here should also be a circle with a center at 0, 1 and a radius of 1. Can't really tell that from the equation, but if you were to graph both of them, they would look the same. All right. So that's basically how you convert, and we're going to definitely have to practice that in class. Okay, let's try converting the other way. We are going to convert from polar got a little extra on my word polar to rectangular. All right, so converting going the other way. Now, this you probably aren't going to be as comfy with because you are just now learning polar over the last couple of days. So there's lots of different things, and there's not always a right direction to go. Every problem is a little different. So there's some real simple ones, and there's ones that are a little bit more complicated. So I can start off with r squared equals 5. That one's pretty basic. If you look back to your conversion box, if you look at what r squared equals, if you come up here, what does r squared equal? It equals x squared plus y squared. So you just take this and you replace it with x squared plus y squared equals 5. And what you see from that is that this is a circle with a radius of square root of 5. Pretty basic. And since everything's in x's and y's, you're done. And part of why you're done right here is that this is the standard form of a circle. So you can stop there. It looks like a normal equation for a circle. Let's look at number 2. Theta equals 45 degrees. Now these are a little bit tricky. For this one, I want you to think about what this would look like on a circle piece of graph paper. Even though I haven't really talked to you about graphing that yet, this is literally saying on this circle piece of graph paper, we want all the thetas that equal 45. All the thetas that equal 45. Well, what's that going to look like on this piece of paper? All the thetas that equal 45. That's every single point on this line. So every single point on this line and that line extended. So what kind of graph does that look like? It looks like a diagonal line. Some of you, I think, can think about what that would be in terms of X and Y, that diagonal line. Others of you are like, how am I supposed to know? So in the end, we are supposed to get the equation of a diagonal line. That's what this one's going to look like. But how do we get there is the main question, especially because if you go up here and look in our conversions, there are three of these that have thetas in them. So I'm going to tell you right now that you are going to want to pick the third one right here because this one is different than the other two. Can you see what makes this one different? What makes it different, friends, is that the third one does not have this R in it. Okay, that's what makes it different. So we are going to use the third one so that we don't introduce an R into the problem. So what's going to happen when you solve this? It's kind of weird, but what we're going to do is we are going to take the tangent of both sides. So it's kind of different. If we had used one of the other ones with a theta, we'd be putting an R in the problem as well, which just complicates life a little bit. So now what's going to happen is we can evaluate the right-hand side. Like we should know what the tangent of 45 is. It's 1, yes. And on the left-hand side, tangent of theta, we can replace using our conversions. It's a y over x. So now you've gotten rid of the theta and you just have x's and y's, which makes it rectangular form, which is nice. But saying y divided by x equals 1 is not the standard way to write down the equation of a line. So you're not actually done with the problem. You need to make this look like the equation of a line. To make this look like the equation of a line, you multiply the x over to this side. So the equation would be y equals x, which math students should know is a diagonal line that goes straight through the middle of everything. So this is standard form for a line. I almost wrote stand form. Standard form. Okay. All right, so that's a little bit tricky, but that's why we practice. All right. And the third type and the last type I'm going to go over with you here, and then the rest will be for practice. If you do one like this, r equals -6 cosine theta plus 2 sine theta. This one's got a lot going on. Looks a lot more complicated than the other two. We've got r's, we've got cosines, we've got sines, we've got thetas, we've got all the things. So in this type, the method for solving here, which is a method that comes up quite a bit, is if we are going to get rid of the cosine and get rid of the sine, the only way we can use our little conversion, I'm going to scroll back up here, is if there's an r in front of those trig functions. So what we're going to do is we're going to put an r there. We're going to multiply everything by r. So we're going to multiply each of these terms by r. What you do to one term, you got to do to all of them. So that's going to change our problem into r squared, which you should be saying, oh wait, that's in our conversion box too. Sweet. And then negative 6 r cosine theta, and then 2r sine theta. And so that works out really well because all 3 of these pieces are in our conversion box. So now you can replace all of them. We get x squared plus y squared equals negative 6. This is x. And 2 times this part is y. That's great. But this equation is not the standard form for anything. You should recognize x squared plus y squared. That is usually part of a circle. We just saw that in number 1. So what you're going to have to do is make it look more like the equation of a circle. The way you do that is you move everything over to the left-hand side. And we did this last year, Math 3. You are going to have to do our little friend completing the square to turn this into the standard form of a circle. So you are going to take half of the 6 and square it and add it to both sides. You're going to take half of this negative 2 and square it and add it to both sides. And once you've done that, you have factorable pieces here. This factors into x plus 3 squared. This part factors into y minus 1 squared. And on the right-hand side, we get 10. And that, my friends, is looking more like the equation of a circle. So now you're done. This is the standard form for a circle. And then you can see, oh, the center would be at negative 3, 1, and the radius would equal square root of 10. So sometimes changing into rectangular is kind of a pain. But guess what? We're done for today. We'll practice in class, and that'll be even more fun. As always, have a pleasant evening, and we'll see you tomorrow.